So continuing for our discussion in section 6.2, in 6.1, in 6.2 we will discuss the transmission line circuit. Now we will officially introduce the transmission line circuit for the case of termination with resistive load, which is probably the simplest transmission line circuit configuration. And from previous result, we have introduced the general solution for voltage and current signal within the transmission line, which is in the form of AF plus EG, where the F function represents the signal or the energy that's going to the positive Z direction, which will be characterized as the forward-going component, and the function G represents the energy goes to the minus Z direction, which will be referred to as the backward propagating term. So based on this result, we can rewrite the transmission line equation for both the voltage and current signal in terms of the so-called forward-going and backward-going part. So V, this V refers to the total voltage on the transmission line for a specified time instant t and a specified location Z. And because the transmission line, as we already discussed, is a one-dimensional geometry, the wave can either goes to the positive, to the forward-going direction or the backward-going direction. So the solution is formed with V plus and V minus, which is essentially the same as the AF part for the V plus and the BG part as V minus. And note that the parameter within the V plus function and V minus function are T minus Z over Vp and T plus Z over Vp respectively. So as you can see from the parameter, they involve both descriptions about the time and about the time t and about the position z. Similarly, the current description, the current function, which is also a function of position z and time instant t, can also be returned in terms of V plus and the V minus part. Now that there is a difference between the current signal and the voltage signal, that is the ratio. Now, the voltage over current ratio on a transmission line is referred to as characteristic impedance. 特性阻抗 characteristic impedance. So the current function is written as 1 over Z sub 0 times V plus minus V minus. So you need to know that there's a minus sign about the V minus part, while the V minus part in the voltage description comes with the positive sign. So to simplify the expression, you can usually we can write the transmission line equation in terms of a 6.29a and b, that is the total voltage V on the transmission line comprise the forward-going part V plus and the reverse-going part or backward-going part V minus. And the total current on a specific position at a specific instant t, I equals to 1 over Z sub 0 times V plus minus V minus. Okay? So take a look of these two equations to memorize the formation, because later on in this chapter we will use this representation to describe the voltage and current behavior on the transmission line. All right? And so So in the previous slide, we have seen that the total voltage and total current are both can both be described in terms of V plus and V minus components. And note that the I description, the total current description I, can be written in terms of I plus and I minus as well. Which were more intuitive 更直觉上的表示了把 I 也把它组合成是看作是正向传播跟反向传播的加总所以你一样是写作 I plus 加上 I minus。但是你要注意的就是 I plus I minus 跟 V plus V minus 之间的关系So you need to be careful about the relationship between I plus V plus I minus and V minus. I plus equals to V plus over Z sub 0. So the foregoing current equals to the foregoing voltage divided by the characteristic impedance Z sub 0, while the backward going current equals to the minus of V minus over Z sub 0. So remark that there is a relationship that the voltage over current ratio shall equals to the magnitude of the current characteristic impedance for both forward-going part and the backward-going part. For signals going in the transmission line, the voltage over current ratio is a constant based on the transmission line geometry, based on the configuration of the transmission line. However, as you have seen that when you combine the two things together, what is the ratio of V over I? Total voltage over total current at a specific position. Well, it's not necessarily equals to Z over Z sub 0. Because as long as you have both positive going voltage going signal and negative going signal, because if you combine the two, you have a minus sign over here. So this result, the V over I ratio, does not equals to Z sub 0. Now, if you have both forward going and backward going components within the transmission line. On the other hand, if you only have forward-going components in the line or only have the backward-going component in the line, then the ratio between the voltage and the current is Z sub 0, is the characteristic impedance. So you need to be careful about this. Individually, they should abide the ratio of characteristic impedance, which is defined by the transmission line. However, the total voltage, total current ratio, it does not necessarily equal to the characteristic impedance ratio. All right? The next thing is to look at the signal on the transmission line in terms of power. All right, so as we already know that the power equals to the product of voltage and current. So therefore, we can define the forward-going power on the transmission line, which is the product of the V plus part and the I plus part. So the P plus, the forward-going power, the electromagnetic power energy that's going to the positive Z direction shall equals to the product of V plus and I plus, which can be rewritten as this by replacing I plus with V plus over Z sub 0. So it equals to V plus to the square over Z sub 0, which is consistent to what we have learned in the circuit theory. All right? And similarly, we can write up the expression for the power going to the negative z direction. That is the P minus par. And by definition, it's the product of V minus and I minus signal. And if you substitute the I minus signal with V minus over Z sub 0, you end up to this minus over V minus to the square over Z sub 0. So it's different by a minus sign. So what is the significance of this minus sign? Well, the significance of the minus sign means the positive power and the negative going power goes to opposite direction. Okay? So the minus sign represents this energy. This power goes to the minus z direction. All right? So if you illustrate the V plus V minus I plus I minus P plus P minus stuff on this transmission line illustration, you see that at a specific point, you have both the V plus and V minus sign, V minus component, and you have corresponding I plus and I minus component. Note that the direction is defined that they are propagating to the right. So you see that this arrowhead, which labeled with P plus and P minus, they both goes to the right-hand side, goes to the positive z direction. So therefore, the expression for P minus comes with a minus sign that tells you that in fact the power is going to the backward direction. Okay? And 在这里所以 V 正 V 负代表是什么？在这一个传输线上面的两个导体上面的电压差嘛，那 V 正的话当然是往正极方向 ，V 负往负极方向。那你会看到这边还有一个 I 正 I 负，这边也标一个 I 正 I 负，所以告诉你什么事情？这个大概我们在前面第5章大概就有稍微就有提过了这我不晓得你有没有记起来也就是说在传输线上面，它上面走的讯号是一个我们叫什么 differential mode 差分模态的讯号也就是说在这两个导体上，它的那个 I 正讯号，你的 current 讯号会有一个往左走的电流，往左走的，实际上有一个往右走的电流跟一个往左走的电流了，一去一回，所以它的方向是相反，然后大小是相同的，所以注意在传输线上面，我们希望走的讯号是差分讯号或者差模讯号，那你就说，老师，你既然这么强调所谓的差分讯号、差模讯号，那只要不是差分讯号，那叫什么讯号？那叫共模讯号 （common mode）、common mode current， 有没有听过？这种叫 differential mode current， 还有一种叫 common mode current。举一个例子好了，大家不是看到台电的那个高压电塔的，不是看到的不是很舒服吗？对不对？特别假如说那个电塔在你家旁边，但是台电跟你讲说，从学理上计算，高压电塔所产生的电磁场是很弱的，比你的地球背景磁场强度还要弱个大概只有地球背景磁场强度5%之类的吧。那他说的这句话对不对？学理上是对的。但所谓学理上是对的，是说，在这个高压电塔上面，这个60赫兹的电压电流讯号，它是差模的。那怎么验证这件事情？安培右手定则你看到那个电塔上面的电线长什么样子？2根嘛，当然还有第3条吧，还是什么的主要就是那2根嘛那上面电流一去一回嘛。那一去一回的话，你假如用安培右手定则，它所产生的磁场怎样？方向相反的所以除非在那2条线中间，那2条线中间的磁场是很强的只要是跟它的那个能量密度 有关的，但只要是在那2条线之外，你的磁场是互相抵消的。OK， 所以插膜的电流它所产生的能量是被它所传导的插膜电线，所以你看到那个电线电塔的那个2条线的那个电线，虽然它是开放式的，但是它还是传输线的一种，它的能量是被锁在那2条线之间的，在那2条线以外的地方，其实电磁场是很小的，你可以用安培用手定则验证，它们是互相抵消的，所以即便它是开放式的，但是假如台电送出来的电不是那么的漂亮，而有一点所谓的 common mode， 也就是同向的那个成分在的话，那你用安培用手定则比一比，你会发现它那个是没有办法抵消的，所以就变成说，它送出来的那个电的成分，假如是完完全全 ideal 的差分电流的话，那它其实没有能量会漏出来。但是反过来讲，它有一点点的共膜的成分 （common mode current 的成分的话，那其实对周边的背景电磁场就会有影响，就会增加。好，所以一般的传输线上面，基本上我们走的也是差分模态。理论上不应该出现所谓的共膜模态。假如有共膜模态的话，它就从传输线变成什么？变成天线了。我们在做天线的时候，其实就是要把能量甩出去让它能够往空间中辐射。那其实要让电磁波、电磁场的能量往空间辐射，它需要的就是 common mode current。也就是在那个环境底下，只有单一方向、同一方向的电流，来回震荡的电流，这种 stand-alone 的这种 common mode current 呢，就可以有效的把电能转换成电磁波形式的电场磁场能量，往外界传播。OK。好，那这边我们看到的是第一个你看到的第一个传输线电路So this is very fundamental transmission line circuit。每次看到这个电路，就让我想到几年前了接近30年前了。在美国第一次上研究所的课的时候，你上那一课叫 microwave engineering 微波工程，然后上课的老师是一个法国人，当然因为在美国嘛，所以他当然是讲英文嘛，OK。只是说这个法国老师呢，他大概只有前面10分钟讲英文，后来就自动转成法文了也不是真的法文就是法文腔很重的英文OK。然后那个时候他放的就是这一个图片，然后那当然那个时候第一次是听英文上课嘛所以你看你比我早了好几年，第一次上EMI我那个时候25岁才第一次碰到EMI的课OK。然后就看到这个电路，他就解释这个电路然后他讲着我就有一个词我一直听不懂，但是他一直讲那个词，所以就表示那个词很重要。他就讲 Ginny Hado， 我就看着电路说，我看什么东西是 Ginny Hado。后来看着我大概听了他讲了大概10几分钟之后，原来那个是 Ginny Hado。OK， 这里头哪一个是 Ginny Hado 的？电源虽然你看这个写 R 什么 RG 嘛，对不对？那个 G 字的又是 Ginny Hado英文叫做 generator 只是因为他法国人嘛，所以那个 generator 念起来就变成 Ginny Hado 了OK。那有人学会法文嘛有的话大家就知道我在讲什么了好啦，所以很厉害上课你听不懂就是词语的单字听不懂是正常的啦正常的，但总是习惯就是一个习惯嘛对不对？所以后来那个老师，即便他是讲法文腔的英文， 也是慢慢去习惯它吧，好不好？所以左边这边是 generator side and the left hand side is the generator side, which contains the signal source. And in this case, which is a more simple condition, we have a constant voltage source. However, in general, this can be an alternating voltage source or alternating current source, which means the voltage and currents provided by the source can be an AC source, can be an alternating one. So the internal resistance comes with the generator is labeled as RG. So this is the internal resistance of the generator. And on the right hand side is your termination. So as the title of this section, terminated by a resistor. We see there is a resistor connected to the right end of the transmission line and is labeled as RL. L stands for load. 负载 RL. Here is RG, stands for generator. And in the middle is your transmission line, which can be a coaxial cable or a microstrip line or a waveguide, as we can see from your textbook. And for the transmission line part, you need to specify the characteristics of this transmission line. And in general, you need to specify a couple of the specifications, including the characteristic impedance Z sub 0， 叫什么？特性阻抗 Z0 ，Z0 是特性传输线的特性阻抗，代表什么？上面的电压电流讯号比值 ，alright？ VP stands for velocity of propagation or velocity of phase, which suggests the propagation speed of the E and H field or voltage and current propagation speed on the transmission line. And you also need to specify the length of the transmission line. So in this figure, you have the left end left as Z equal to 0, while the right end labeled as Z equals to L. So L is the length of the transmission line. And sometimes in later part of this section or this chapter, you may come across transmission line length description as 1 microsecond, 100 nanosecond. The length is described in terms of time. What is the significance of this description? 就像你在讲1光年是时间的单位还是距离的单位？1光年是距离的单位这代表的是光在自由空间中跑1年的长度叫1光年嘛，所以光年虽然听起来是时间，但它实际上是距离的描述。所以有的时候在传输线的描述上面，它会说这一条传输线的长度是10个 microsecond， 那意思指的是什么？意思指的是电磁讯号在上面跑，从左边跑到右边要10个 microsecond， 有的时候会这样子表示了当然，你也可以把它的传播时间用什么？用 L 乘上长度乘上乘上 VP 了因为 L 等于 VP 除上等于 T 嘛OK。对了对吗？有没有写错？速度等于距离除以时间，我他妈还写错了。OK， 好。所以有的时候，所以传输线的距离的那个传播时间可以写作 L over VP 嘛？我在写对还是写错？这样对了吧？对了。 Right. So the basic configuration of a transmission line circuit comprises the source, the transmission line, and the termination, the load. And, okay, now here comes our first question. Assuming the characteristic impedance of the transmission line is 15 ohm, and it's terminated with a 100 ohm resistor. So what is input impedance? Input impedance, 输入阻抗 at the left end, at the position of z equal to 0. What is the input impedance? Of course, you should guess about the answer. What is your answer? Well, the answer is depends. It depends on what time you are looking at. If you are looking at t equal to 0, which means the switch closed on. If you look at the time instance that the switch closed on, and you are stand over here and look to the right, what is the impedance that you observe? Well, if this is the case, t equal to 0, and you look to the right, the answer is 15 ohm. Why? Because you, as a small ant, 小蚂蚁，把自己想象一个小蚂蚁 stand in front of the long transmission line. The only thing that you can see is the transmission line placed in front of you. So the characteristic impedance of the transmission line is the input impedance you observe at this moment, at this very moment, is 15 ohm. Okay? However, if you are asking me what is the input impedance observed at this position at time instances 1 second, 2 seconds, 10 seconds, if the time is sufficiently long, then the termination, I mean the resistor placed at the right end, comes into play. Because the signals will what? Will bounce back and forth on the transmission line. At the moment that the switch closes on, you have voltage signal goes from left to right, and at the end, you have a so-called mismatch, impedance mismatch, 阻抗的不匹配。Because the voltage over ratio on this side, on the left-hand side, at this intersection is 50. On the other hand, the voltage over ratio across the load, which is a 100 ohms resistor, should be 100. So you have impedance mismatch. And the result of impedance mismatch is that you will produce a refracted signal from the right-hand side. So there is a signal that we shall refer to as V minus. So when the switch closes on, you will first have a signal goes from left to right and is labeled as V plus. And when it reaches to the right end, you will produce another signal referred to as V minus, due to the mismatch in the impedance at the right end. And what happens when the V minus signal reach to the left-hand side? Well, it depends. If the internal resistance of the generator, I mean the RG, does not equal to 50 ohm, you will have another mismatch at the left end, right? Then you will produce another signal, which in this textbook is labeled as V minus plus. So what is the implication of this labeling? Well, it tells you that it goes to the right. However, it comes from a signal goes to the right, to the left. So this signal is referred to as V minus plus. And again, when this signal reaches to the right-hand side, again, you have impedance mismatch. So you will have another signal labeled as V minus plus minus. Right? So the labeling rule is quite straightforward. So what happens next? Well, you have another signal V minus plus minus plus. Right? So on and so forth. Okay. So this thing will continue. Then you say, okay, come on, will that be too complicated, too much trouble because this generation of follow-on the signal bouncing back and forth between the transmission line and it will keep going forever, right? Yes, it will keep going forever theoretically. However, now that you have a resistor attached to the right and another resistor attached to the left, what happens with this resistor? Well, the resistors, they absorb energy. So the energy provided by the voltage source, part of the energy will goes into the resistor. Goes into the resistor. And as a rule of thumb, or in general, these are referred to as higher order terms, 高阶项, higher order term. And because the two sides are terminated with resistors, which means they absorb energies, and the difference will become smaller and smaller. So higher order terms, the magnitude of higher order terms will go down eventually. So eventually, you will reach a so-called convergence or saturation on the transmission line. So providing that the observation time is long enough, the transmission line effect, that is, the things that I have just described, the signal bouncing back and forth within the transmission line goes away, will be converged, will saturated. So eventually, you will only see the resistance of the load. It will comes back to circuit theory. 也就是说你在电路学里头学到的稳态分析啦，或者我们这应该叫稳态分析。所以在今天这一章第6章里头，我们讲的是传输线的时域分析。我们从 time domain 的角度来去看传输线的现象。所以我们接下来要看的是在传输线上面发生的叫做 transient 暂态。所以我们会把讯号的那个电路上面的那个开关关上去，也就是让它产生一个状态的变化。在开关关上去之前，我们假定在这一个传输线上面是没有电磁讯号的，没有能量的。关上去之后会发生什么事？这一个左边的电池，当然这边是一个单纯的 DC 电池，它会怎样？会对右边的传输线电路充电，提供能量。那怎么样提供能量？就像我们刚才所描述的，它会有一个 V 正的讯号 ，V 正的讯号跑到右边会有弹回来 V 负的讯号，然后再弹回去 V 负正、V 正负、V 负正负、正负正负，这样一路下去。理论上他们会维持无限长的时间，但实务上呢，这些高次项会越来越小。所以它的重要性会慢慢的，不是慢慢的，其实会快速的衰减嘛。所以大家来回撞来撞去，撞个大概3、4次、4、5次之后，它其实就进入所谓的稳态。所以当你进入到稳态的时候，它其实也就是说你观察的时间够久，那么传输线的那个暂态的效应就会不见了。所以进入到稳态之后，它的分析就类似一个单纯的电路分析，也就是说，你这里头的电路在进入到稳态的时候，这个电路其实可以被简化成一个电池内电阻接上一个负载电阻，就这样而已。 Rg 跟 V0。那你说中间的传输线呢？在稳态的时候，传输线的效应是看不到的。好，但是在站态的时候是很重要。所以其实就看你的这一个讯号源的性质。假如现在讯号源是一个 DC 的时候，但是我相信各位在学电力系统或电机机械的时候，大概也会知道，当你的系统的电路系统的站态突然产生变化的时候，会有一些上面讯号会有一些扰动嘛。就是说你学的深入一点的时候，是要去研究这个问题的。但是假如在纯粹的稳态的分析里头，其实你是看不到传输线效应的。但假如说这一个讯号源被改成是一个 AC 的一个讯号源，然后里头走的讯号是一个快速变动的射频 RF radio frequency 的讯号的话，那其实传输线的效应就会一直在那边。那这个这个部分传输线效应的话，我们会在第6章跟第7章来讲。只是说第6章我们从实例，也就是站态分析的角度来去看。我觉得先看它里面的东西是比较方便你去理解这一个讯号在传输线里头所进行的变化，比较容易在物理的方式上去理解它。不过第7章讲的是 frequency domain， 我们叫做频率的分析啦。那第7章的内容是实务上比较有用的，或者比较方便使用的。假如你对于射频电路有兴趣的话，未来走微波工程或者射频相关的话，其实我们大部分用的分析方式还是在第7章教，也就是 frequency domain 上面的技术来教。OK， 好。有同学在Ruby那边问我说还有没有收专题生？不好意思，我收满了。OK， 所以大3这一届已经在开始了。OK， Alright, so here are some basic assumptions about the transmission line circuit. We assume that there's no voltage and currents on the transmission line before t equals to 0. So when t is smaller than 0, the transmission line system is fully uncharged. So there's no voltage and current signal reside on the transmission line. And we wish to discuss the transient wave phenomena. 我们刚才讲的站态分析了transient 的电磁传播transient wave phenomena on the line for t greater than 0, because at t equals to 0, the switch goes on and the battery or the voltage source, the DC voltage source, will start to charge the transmission line in terms of the so-called V plus signal. So and you notice that the transmission line is described in terms of the characteristic impedance Z sub 0 and the velocity of propagation Vp. And when the switch is closed at t equal to 0, a positive going wave, a foregoing wave, originate from the left side, that is Z equal to 0, will start to travel toward the load, travel from left to right. And the question is, what is can you figure out the magnitude of this V plus signal, or the foregoing voltage? Well, it can be determined using simple circuit equations. So we know that we have V plus signal, voltage signal goes to Y, which come along with I plus current signal to the right. And what is relationship between V plus and I plus signal? Well, the ratio should equals to the characteristic impedance Z sub 0. So you can write up this equation. That is V0 minus I plus times Rg, the internal resistance of the generator, minus V plus equals to 0. So which is a KVL equation, and a voltage equation based on the Kirchhoff voltage law, that is the overall voltage drop on this loop is 0. So you have V0 minus I plus times RG minus V plus. Okay? And because V0 is known, RG is known, and the V plus over I plus ratio is 50 ohm, that is Z sub 0 is known as well. You can find the description, you can find the solution for V plus and I plus using this equivalent circuit at this position. So this is the equivalent circuit at the left end at the moment of t equals to 0 plus 当开关关上之后在那个左侧端你就可以画出一个这样子的等效电路，从这个等效电路里头写出那个 V plus I plus V plus I plus 因为是 Z 0倍嘛所以它其实是可以写得出来So the actual formulation for the V plus signal and I plus signal can be expressed in terms of equation 6.34a and b. Alright? So now you have the foregoing voltage and foregoing current description. So what happened next? What happened next is when the signal goes to the Ym, that is, at the position of the load resistor. Say you need some time for the signal to propagate. And the time required can be expressed in terms of the length divided by the speed, the voltage, the velocity, L over Vp. So I'd like to encourage you to think that your lecturer, Professor Liao, if I vanish at this very moment, when will you notice that I disappear? Well, you might never notice because you are looking at your phone. On the other hand, if you are looking at me right now, when will you find that I disappear? Well, for the student sitting in the front, it may be around 10 milliseconds. And for you guys sitting in the back, it will take you probably 30 milliseconds to notice that where's our lecture? 所以假如我现在消失的话，现在不见的话，其实你没有马上看到你要隔差不多10个 millisecond 或者是30个 millisecond 才会发觉到嘛，对不对？为什么？因为你看到的我不是我发光了OK， 是光打到我身上反射的光而光的行进是需要时间的就像说，你可以跟你女朋友说，就算现在太阳消失了，我们还有8分钟能够抱在一起对不对就是说。这个重力啦，还有电磁波的传播是会有时间延迟的，这个计算其实就是在算你的传播的时间延迟所以等于什么？延迟时间等于距离除上速度嘛L over Vp. Okay, so at the moment of t equal to L over Vp, the I plus and V plus signal will arrive to the right end. However, assuming the characteristic impedance of the line is 15 ohm and the termination is 100 ohm, and you know that 50 ohm is does not equal to 100 ohm, so you have impedance difference, which means the voltage over current ratio are not consistent on the line and on the resistor. Therefore, to meet the boundary condition, to satisfy the boundary condition, when the I plus and V plus signal reaches to the right end, it shall produce a refracted signal, say V minus and I minus. then the overall voltage over current ratio, that is V plus V minus divided by I plus I minus, this ratio should be consistent with the load resistance, RL. So you have this RL to write up the relationship between your incident wave, incident signal, V plus I plus, and your refracted signal, V minus I minus, so that the boundary condition can be satisfied. Right, so in this slide, we can write up the equation. So the total voltage across the load resistor, that is V plus V minus, equals to RL times I plus I minus. And based on this relationship, that is based on the boundary condition, you can write up the expression for V minus and I minus. All right? So also, you know that I minus equals to the minus of V minus over Z sub 0. So you can write up the expression with some manipulation with those equations. You can write up the equation of this, V minus equals to the V plus times RL minus Z sub 0 over RL plus Z sub 0. And here I will introduce an important parameter, that is the voltage reflection coefficient, which is in general labels in terms of gamma, Greek letter, capital Greek letter, gamma. This is referred to as the voltage reflection coefficient. It can be defined in terms of V minus over V plus, the reflected voltage over incident voltage, V plus. And it shall equals to RL, the load resistor, minus Z sub 0 over RL plus Z sub 0. 好，在电磁学里头，我让你背的东西不多，这个是少数我让你背起来的。反射系数，好不好？反射系数的定义，请你先背好、记好反射系数的定义。反射的电压除上入射电压 ，V minus over V plus。再来就是它的系数，它的那个成分。所以你会看到这是两段的阻抗啦。两段的阻抗，前面那一段叫做 Z0， 后面那一段叫做 RL， 或者有时候我们写的 Z1、Z2 啊，不管了，在这边我们先用 RL 好了哈。那因为下面分母的地方是相加的，所以你先写谁没有什么关系，但是上面分子的部分是相减的，所以请你务必要记好顺序，好不好？你看你的那个期中考的考卷基本上，你只要写的大概有一点样子，我大概多少会给你一个分数。但有一个状况就是说，那个东西应该是向量的，你写成存量，或者该是存量你写成向量，我是全扣，好不好？我对这件事情无法容忍，因为我已经跟你讲了很多次，好吧？向量、存量搞清楚，好不好？这个也是一样跟这个相关的反射系数相关的计算。假如你连这个左右的那个顺序都没有搞清楚，都记错的话，那就全扣了，好不好？让潘天来行公一套紧所以你们记得我们在算反射系数因为反射系数是其实像这个还单纯这个是传输线接到一个电阻，我们以后还会看到说，是因为有传输线1跟传输线2。传输线1跟传输线2的时候呢，你会左边看过来有一个反射系数，右边看过去有个反射系数，这两个反射系数还不一样，所以那个记的顺序要那个标的那个阻抗的顺序，请你要记好，好不好？看过去的在前面，看过去的减这边的，所以这是看过去的嘛，你从这边看过去是 RL 嘛，你自己的地方是 Z0。所以在写反射系数的时候是看过去的扣我们自己这边的RL 减 Z0， 好不好？这个顺序请你记下来，好不好？我花了5分钟跟你讲这件事情， 你要考试的时候，这边这个再写错那种。OK 好。那课本上除了有电压的反射系数，其实还有定义一个电流反射系数，但你不要理它好了，我们就记电压反射系数就够了，好不好？好，我们就记电压反射系数，免得你搞混。OK 好，所以电压反射系数的表示式就是 V 负 over V 正，L 减 Z 0除上 L 加 Z 0，好不好？拜托你背下，多看几次啊，把它记下来。好，我们先休息一下。